Okay. This is what we have left. And then we're done. It's not so bad, right? How was last week? Other than the obvious. Was it nice? Didn't have to come on Tuesday. One lecture, that's pretty good. Didn't have to listen to me. That's pretty good. That's all three, really good. So this whole section on comets, collisions, small bodies, how comfortable do you feel with that? Raise your hand if you feel super comfortable in that. Because I don't really know how we're gonna do today. I'm like just throwing shit in the air and we'll see what sticks. Because I don't know how much you got through. I don't know how quickly you got through it, right? So it's kind of hard for me to just like assign a homework, not knowing where you are as a class. So, oh, okay. So very minimal stuff. Is that correct? Okay, and maybe that was the vibe. You never know. Okay, so there is slack. I always build in like space for classes to slip a little bit. So we could say to ourselves, exoplanets, who gives a fuck? And we could just like sort of do this in a little bit more detail today, like slide this stuff down, and then just go into it. If you want no bonus lectures and you want exoplanets, we can do that there. If you say to yourself, no, I really want to learn about radioactivity, or I really want to learn about whether or not aliens exist, we could have a whole class on that as well. Usually I don't like tell people like to voice that opinion until about Turkey Day. Because that gives me enough time. Unless it's like a brand new lecture that I've never taught before. That tends to be rare. So for this week, I guess by a show of hands, who wants to just start here and then see where the class is as a whole? Okay. Who wants to start here and see where the class is as a whole? Okay. Who wants to start here and see where the class is as a whole? All right, that's one person. So they are outvoted. Okay. Sorry, maybe that's a sore topic. People feeling a certain way about the election? Yeah. Yeah. Not a good way, potentially? Yeah. Okay. So as a state employee, there are certain things that I'm not allowed to tell you, right? So as a person who works for the state of California, I cannot advocate for or against certain candidates or elected officials. But I am a person, right? Surprisingly. So I exist outside of the classroom. I have my own feelings. And, we can talk about maybe there's a correlation between the fact that, like, since Trump was elected, the sun seems to be going down earlier, gets darker faster. So, like, I don't know. And the trees keep dropping their leaves. Coincidence? I don't know. Okay, so that's a coincidence. We understand how that actually works. But one of the things that we do want to keep in mind is that even though it feels potentially very disheartening to realize that maybe a majority of Americans in different parts of the United States don't share your beliefs, it is important to recognize that we live in California. And California has very robust laws, and the states have a lot of internal rights, right? California is the 6th largest economy in the world if it were its own country. Our governor, love him or hate him, he can be a weirdo, he can be sort of a sociopath. He has said specifically that he will not allow the federal government to overreach and to do things like deport family members, do things like pass restrictive abortion laws, pass restrictive laws against people's identities, right? So it's not great if you're in one of these protected classes or you're thinking about a family member in the rest of the country who is. But know that for you right now, right, we can be grateful for where we live, right? Even if we don't always agree with, say, like 40% tax. It's the cost benefit analysis there, right? Okay. I'm not allowed to keep talking about it, but if you want to talk about it outside of classroom, happy to. Okay. So let me open up. Oh yeah, one more thing. So now let's talk about what we're supposed to be doing. So this homework, I guess we'll focus on this stuff, but it'll be due, wait, shit, this is us here. This is us now. So this will be due, I guess, here. I'll just switch it by a couple days so you have an extra weekend to work on it. And how many people have a check-in ready to go? Raise your hand. Okay. That's great. I'm impressed. That's wonderful. It was requested. So that's awesome. Is that a question? No, okay. You're just okay. You may have noticed that the homeworks are not coming back to you. Yeah, so that's really hard to write about how well you did on the homework when you don't have them back. I think I have up to like 5 here. Apparently the grader, just life gets in the way and they're going through some stuff right now. And I did not catch that soon enough. So I will make sure all of the grading up to 9 gets done this weekend. You've turned in 9 here, or whatever the rest of it is of 9, right? This is whatever anyone else wants to turn in 9 will be here. So I will make sure they all get graded. But since you won't get any of that back, I feel like it's kind of like, what are we doing here, right? This is the unfortunate thing with going away from online homework. I get to hear a little bit more of your voice, but you don't get any feedback on that if this other part breaks down, right? Okay, so that's my responsibility. So I don't feel like I can punish you with this deadline. Is that fair? Okay. So I will try to get them back to you. If this moves to like here or even here, is that reasonable? Like if I can get you a majority back by Thursday, not all of it, but a majority, and then we try and do a check-in next Tuesday, a week from today. We'll agree to that? Okay, and if you're done already, you're done. I'll take it right now. And I can give you feedback on it right away. Okay. Everyone in agreement? Okay. Good. Then let us pull up some slides this fall, hopefully. Nope, different class. Oh God. What's happening? Okay. Okay, so you saw this. Yeah. Homework 10 will be due on Tuesday, a week from today. Nothing is due in 2 days. And I'll update the calendar. Yeah. Homework 10 and check-in are due next Tuesday. Yes. Yeah, that would be helpful. And if there's no homework for you by Thursday, yeah. What was that? Let's go with that. That'd be a much more polite way of saying it. Okay. What's this? Comment. So now the good thing is you've already seen the material, so you're gonna come in like experts, right? Okay, you know what the 3 things we're looking at here are? Yeah, tail, right? Good. Oma. That's a fun word. What's that mean? Oma?
Is it dusty atmosphere?
Yeah, dusty atmosphere right there. Good. And there's two tails, right? You know which is which? Yeah, so one of them is like the basically plasma or ion tail, and the other is dust. Well, I don't know which is which here, so I don't know what it's saying. But one of them is one. The curved one tends to be the ion. Okay, is this a comet? I see some no's. I don't see any yeses. Okay, you already saw this slide? Okay, all right. So you learned about asteroids. What's an asteroid? What? Leftover pieces of rock. Okay, so if we look here, that's the sun, not to scale. What's the next one? Mercury, Venus, Earth, Mars, asteroid belt, Jupiter. And just in between Mars and Jupiter is a whole bunch of stuff that could have been a planet. It wanted to be a planet. It was doing its darn best. And Jupiter was like, nope, and just kept breaking it apart, pulling it apart, shredding it until you get this nice little disk. Remember, we were talking about disks around gas giants, like Saturn's disk, Jupiter's disk. And we said that Saturn has a really beautiful disk because a moon got too close and got pulled apart. It's almost like that, except for it never formed into a big object. There is one big object there called Ceres, and that's big and circular. But a majority of them are quite small and not circular like this. There's Ceres. It's like big, right? Yeah. No, not unless you get rid of Jupiter. Jupiter will always be pulling it apart, right? If Jupiter hadn't formed there, they would coalesce and they would form a small body. The total mass is less than, say, I think even the moon. It'd be smaller than the moon. But you could take all of this stuff, clump it all up together, and you get a little small body. Okay. There's Ceres. There's Palace. This is a great naming system, right? 1, 2, 3, 4. That's the order in which we found them. Okay. There's their relative sizes. Ceres 1, Vesta 4, and they get bigger and smaller as you look here. That's the moon. You saw this one already? Okay. And you see down here, you get these really, really small ones. So you can't see it, but there's a dot inside of that circle. It's small. You can look up my number. So if you look in the small body database, you can find, I should have written this down. Damn it. It's one time to flex on you in the whole class time. So you can look up, they give these asteroids names. So this is the name, and sometimes they're named after people who do work in planetary science. And I am a person who works in planetary science. So I got one. And you can look up the size and you can look up the reflectivity. And then, of course, if you're a planetary scientist, one of the fun things you can do is you can be like, oh, like, how big is your asteroid, right? And so Dr. Whitney, who was here last week, she has a bigger one because she's, older, she's done more things, more impressive. But you can also look at the number, right? So if you get them earlier on, they tend to be higher number. They tend to be larger, but sometimes you get really lucky, right? And you're like, oh, well, mine's like made of gold. No, you don't know that. But you just assume that if it's more metallic, that it's more made of gold. It's not. You don't get rights to it, so it's not like I own it. It's just the name. So if in like 2,000 years, we turn into some civilization that goes and mines the asteroid belt, right? Then I'll have a little flag that'll say my name on it, but I won't have any of the mineral rights for my grandchildren, right? Grand dogs, whatever. Okay, cool. Yeah.
There was actually on Google 30,537 on the payroll for money. One movie knows like 2001 Part 8.
Yeah, how good that is? Okay, so what's the side? That's got to be at least one extra credit, right?
I didn't think of the side. But
Okay, if you could find that and then compare it to Dr. Woodney's, that'd be great. All right, so you saw this already as well? This one? Series? You liked series? What's that? Yeah, it's ice, right? So Ceres actually comes from a part of the asteroid belt where water could condense. And so its density is about 2 grams per cubic centimeter. That is more than ice, but less than rock. So it's this ice rock mixture. And that's not to say if you drill under the surface, you're going to find an ocean like you would at Europa. It's like if you dig under the surface, you're going to find snow, right? Now it's like weird icy snow, but like that's exactly what you see here. This is a surface that's been exposed by a recent meteor hit. And instead of magma coming up through the surface, it's ice, right? And as it gets exposed, it sublimates and it breaks away the material. It's not very stiff material, it's very thin. And as it is exposed to sun, it creates more places where gas can be liberated from the surface, and that takes with it gas and dust and just makes that hole a little bit bigger. Make sense? It's not volcanism. It's not cryovolcanism. It's not liquid underneath the surface pushing up. It's like weak crust showing snow underneath. Cool. Cool video. We went there. I mean, not me and you, but you know, humans. Okay. You learned about this? Okay, just tell me when to stop. Okay. So this is, if you look at this image right here, okay, I want to draw a distinction between how we think about the asteroids in the asteroid belt. So this is a representation. Each one of these dots is an asteroid. Now, of course, they are not to scale because otherwise you wouldn't be able to see a lot of the dots. But this gives rise to this impression that like if I were to fly through this, I would hit a lot of them. That's not true, right? You don't have to dodge anything as you go through the asteroid belt. But it also looks like there's not really any structure. It just looks like, I don't know, you get past Mars and it's just a lot of stuff, right? But if I instead represent it with something called the semi-major axis or the period, how long it takes to go around, then I see structure. So over here is the Earth. It takes us 1 year to go around. There are very few asteroids that live with us. Maybe the moon, if you want to argue. Okay, there's Mars, takes 2 years. There's 3 years. 4, 5, 6, 7, 8, 9, 10, 11, 12. That's Jupiter. Jupiter is right here. Jupiter has a group of asteroids that also go around the sun at the same rate that it does. This one here, they go around twice as frequently. This one here goes around 3 times as frequently. This one here goes 4 times as frequently. And you'll notice there's these little numbers, 1 for 3. So Jupiter goes around once for every time this guy goes around 3 times. And no one lives there. But if I go just to the left or just to the right, then I have lots of asteroids. And the reason for this is the same reason why when you're pushing, your cousin on a swing, you want to wait till they come back to exactly the same place to hit their back, right? You just chaotically hit them. That's like how kids do it when they're first learning, and you don't get off the ground. If you want to go all the way around the swing, you got to hit them at just the right time, right? That's the idea of resonance, right? Hitting at exactly the same time. These are places of resonance with Jupiter. And this is why no asteroid can live here at the 1-3 resonance, because they will keep getting hit by Jupiter, and that hit will build and build and build and cause it to go in or out. And as it goes in or out, it's going to smack into other stuff. So stuff here, safe, happy. Stuff here, unhappy, about to die. Make sense? Okay. I said all that. Look at me. I don't even need the slides. I guess I should have done this. That's the gaps we saw from earlier, right? But before we saw, for example, there'd be like a little moonlet that was pulling or clearing a part of the orbit. The one who's doing the pulling and clearing is this bully out here, right? Jupiter is a bully in the solar system. Don't let anyone tell you otherwise. Okay. Jupiter is responsible for like all of the bad stuff we see. Okay. This is the groups. So there's Jupiter. No one wants to be friends with him. You can tell why. It's bully. And then over here is the Trojans. They like follow behind him. And then the Greeks are running away scared in front. Right? And over here, we have all of the asteroids at their actual positions from whenever this was made. And then you have these fun ones. They're called Hildas. They don't actually do this. They don't go back and forth like this. But when you rotate, it appears like they do. Because all of them are still going around the sun, right? They go like this, or they go like this. But they spend more of their time out on this trajectory. Does that make sense? There is a department called the Division for Planetary Defense, I believe. And their whole job is they want to make sure that they measure each one of these dots that crosses that line. Why would that be important? Which one? Yeah, ours. That's the only one we give a shit about, right? We don't care about how many cross this line. In fact, we want them to, right? So this one here is the one that we care about. Because even if something that's, say, 100 meters were to hit the top of our atmosphere, it'd be a bad day for capitalism, right? Make sense? Yeah, how's it the economy not going to be good? Okay. So you did, let's see if you did this already. You did this? Okay, prove it. You did it with your fingers? Oh, because she didn't have her clicker. Okay. So should I read it off or do you guys remember it perfectly?
Who remembers?
Do you remember it? Okay, 5, 4, 3, 2, 1. Okay, interesting, interesting. So maybe not everyone was here on Thursday? All right. Why don't you turn to someone who has the right answer and see if you can find out what that is. So if you didn't find out, just find a friend. And if everyone around you has the same answer, you probably have the right answer. Yes? All right, what's the right answer? Someone who hasn't talked today. Why?
Since the asteroids are like kind of, I mean, since they're like kind of orbiting with each other, like in the bottom photo, they kind of also like orbiting on the planets, kind of following them. The planets don't have a circular orbit; they have an elliptical orbit, and the asteroids are following.
Yeah. So your example would be like the Trojans, right?
Yeah.
So like they're not like humped like this, they're like going around the sun, they're like that. Okay, good. That's exactly right. So the idea is that asteroid orbits are elliptical, and that's not being shown on the one at the bottom here, right? You're not showing the orbit ellipticity. Okay, cool. Did you talk about this? Okay, this is a fun one. This is showing you big asteroid series, smaller asteroid, Mateo Cosmani. Right? I get to do that now. I'm down here somewhere. And this is how many there are. So there's a lot of like, have you, I don't know if everyone's done this, maybe this is just a me experience. Let's say you take some rocks home from a hike and you put them in your pocket and then you pull them out later and it turns out it's not like a really hard rock. It's like a really like chossy, like flaky rock and like breaks. And so like, instead of having the one cool rock that you thought you had, right, you end up with like smaller rocks and like a lot of them. And then you like do this and oh shit, and you have all of this sand, right? So there's a lot more particles of sand than there are big rocks. That's good. It wasn't about food this time. That's good. Okay. You talked about these? Yeah? Real picture or fake picture? Raise your hand for real. Raise your hand for fake. This is a real picture. I know. Comets go crazy like that. So this is a long exposure, just a few minutes, but you're rotating, or I guess it's not a few minutes. Must be shorter than a few minutes because it's not quite streaks yet. See how these aren't dots? They're kind of like long. Not quite a few minutes. I would say probably 5 minutes, maybe at max. You talked about the parts of a comet. So there's three main parts. There's the nucleus, which is, we're going to zoom in here. That's the interior here. There's a coma of escaping gas that's illuminated. There's two tails. There's the dust tail and the plasma tail or the ion tail. It appears to move away quickly from the sun. It's just drawn away by the sun's magnetic field. And then dust has some fun properties that I may or may not have included here. I study this part. So this stuff hits the top of the Martian atmosphere, and I'm like, cool, meteors. Okay. You saw this one?
Think about this. Can you put on photos on it?
Probably.
Yeah.
Which one?
That's actually the true long and not that.
Wait, this one is Trumov, or this one is Trumov?
Seeing that big picture on the left is also true.
This one?
Something like that. That wasn't eight.
Okay. I mean, I think I have the reference right here. Yeah, I know she thought that Pluto was a planet, but listen, okay. We have definitions in this classroom for a reason. Okay. I will double check. And if this is wrong, I already owe her chocolate, but I'll give her more chocolate. Okay. So you can see that these aren't very big, 5 kilometers. Now that's large for you and I, but remember, how large is the Earth? In diameter? About 12,000 kilometers in diameter, about 6,000 kilometers in radius. So small. And in fact, when we look at an image like this, did you see these ones? So this is the one that we went to visit. And this is what it would look like right before it destroyed LA. Right? That's where I live right there. And then that's me in shock. So this would kill everyone for sure. But this is the right scale, right? So like, I don't know, it would take an hour to drive around. So you could drive. You can't drive on this thing because you'd fly off of it, but does that make sense? Okay, let's go back and scale really quickly. What kind of features do you see? Geologic features. Impact craters? Anything else? Yeah, it looks like a canyon or something here, right? That's cool. Anything else? Tectonics, weathering, erosion? No, none of that. Okay. Okay. So let me switch over. That was good. We didn't do the lecture tutorial. That's fine. We're not going to cry about that. Let's do this one real quick. More comets. Oh, wait, whoops. Enable. Real or fake? Real. That's a real photo. Isn't that really cool? This is from the Southern Hemisphere. This is before I was into space. This is 96. Amazing though. So this is the dust tail, right? You can tell because it's curving. And it's massive. This is I forget the name of it. I should have looked that up. Fuck, whatever. Sue me. Anyone know what this is? Good. Is that all it is? Hold on. Yeah, do you see anything else?
No.
Oh, right there. What's that?
Oh.
You can't see it? Oh, yeah. Look on this one. Yeah, that's the moon and the Earth to scale at the right distance.
The thing on the corner something?
This too?
No.
Oh, that? I don't know what that is. Sorry. Yeah, sorry. I wasn't trying to distract you with other things. No. My bad. Okay. I don't know why I added that, but that's in there. Okay. Okay. Here is that same comet. This is the comet. I don't know how to say the name of it. Yeah. Yeah, so we're going to talk essentially about how that happens right now. So we have this object that's icy and dirty, like made with dirt, so to speak. And what happens is that they occur in layers, like one on top of each other. And when it's very far from the sun, it just sits there doing nothing. Just a big icy rock. But then as it gets close to the sun, the surface heats up. And what you see here are jets coming off of the surface. The surface is being illuminated here. And you notice that's where the jets come out. On the side that it's dark, no material is coming out. So what happens is the gas gets hot and it pushes dust off of the surface. Right? And so this is the way that it's just streaming away gas and dust. So as gas flies off, it carries with it dust particles. But gas is doing the pulling, right? Okay. So you might have structure. Yeah.
How many orbits did this go before it like disintegrates?
Very good question. And in fact, all comets have lifetimes. So every comet that you've ever heard of or seen probably has not gone around the sun more than 1,000 times. Now, for stuff that goes around once every million years, chill, right? No big deal. For stuff that goes around like NK type comets, there are comets, weird, strange comets that go as close as Mercury and then go out. And we know they can't possibly have started doing that at the beginning of the solar system because they would have melted by that point. So something had to have happened relatively geologically recently that changed their orbit and sent them on a trajectory that will now let them live maybe only 1,000 orbits, right? It depends a little bit on the composition. So if you're mostly made of rock, then you can live longer. than if you're mostly made of ice. If you're mostly made of ice, you're going to melt more, you're going to break apart, you're going to become fractions, right? Okay. Here you see an example of what I was just telling you about. So here's that jet coming off of this illuminated part and no jets coming off any of the other sections here. You see this deep little hole, that's an impact crater. But you will see that the surface kind of looks smooth. Why would that be? Did you see the video of them landing on the surface? No? Raise your hand if you saw the video. Okay. All right. So what does the surface look like? Dust? Yeah. I would not call it dust. Snow, right? Like winter wonderland. Okay. Let me show you. We'll get there in a second. You can see in the crater here, inside of the crater, not a lot of smaller craters. Right? So you smash into this thing, and what happens afterwards? I guess it kind of becomes liquidy, like a soup, and then it just flattens out. And there's not a lot of big smacks on it. There's not even a lot of small smacks on it. When we were looking at the moon, when we were looking at Mercury, there would be maybe one big smack and like 50 small smacks. But the small hits aren't present. So what happened? Is it not getting hit with small stuff? Look, got hit by a big thing. Okay, so by chance it should get hit by small stuff. There is more small stuff, right? There's a lot more small stuff. Yeah.
Like eroded away every time it goes around.
It's getting eroded away right away. So let's say we poke a little hole and we show some ice underneath. Remember we saw Ceres? Ceres has that little hole and there's ice underneath. And that starts evaporating when it sees the sun. So if I poke a little hole right here and I show some brand new ice to the sun's going to just excavate it away until it's all the same, right? Just blow away that entire surface. And it's only for larger pieces like this where you sort of punched in, maybe something different happened, and the only thing that changed is that you maybe only eroded the walls as opposed to eroding the entire thing, right? Okay. Here's an example of this process happening. I don't know if you really give a shit about this, but this is the neck. So there's two pieces to this particular comet, and they're connected by this neck piece. And in between the neck piece, we can see how the temperature and the ice are correlated. And so what that means is that where it's hotter here, 5 degrees, lower ice abundances, as opposed to where it's cooler, higher ice abundances. That's maybe not so surprising, right? If it's hot, it melts. So we think of it as this icy, dirty mixture. And look at the percentages here, right? This is like 5% ice. So we don't really think of these as snowballs with dirt in them. We think of them as dirt balls with snow in them, right? Okay. Here's the process. During the day, heats up the surface. At night, you form this like crust, and some of the heat can still make it to the surface. At dawn, sublimation begins again, crust comes up. We landed on this one. This is really funny. You guys know the story already? If you don't, if you do, yourself, I'll just tell it. Funny. They wanted to land there on the X. X marks the spot, cross marks the spot. They knew that they would need to use basically like a harpoon because this object is really small, so it doesn't have a lot of gravity. So I was telling you a little bit about why I went to Paris. I'm working with a Japanese Space Agency, we are going to send a mission to the moons of Mars. Mars has a very small moon. We're going to land a rover on it. One of the problems with driving a rover on a very small object is if you drive too fast, you'll just fly off the moon. Okay? So they have to design this little rover so that, you know, it moves so slowly, it's about 4 millimeters per second, so that you don't move too quickly and fly away, right? Okay. So they had the similar problem, but they're just trying to land, right? They're just trying to get something to stick. Now, one of the problems is that this is a little baby tiny lander. It's not the full spacecraft. It's like a tiny piece that they're gonna try and attempt to land. So they were saying, okay, well, we don't have any sort of like propulsion to like slow us down as we head in, right? With the Japanese mission, we're gonna be able to like navigate all the way down and like land on the surface and then deploy the rover, just have it like drive off. That's much easier to do than what they were trying to do, which is have this little thing go down. So they're gonna use a harpoon, they're gonna stick it into the ground when they land, and then hope that it doesn't bounce. Okay. So let's see how well they did. Okay. Here's the guy. And his name's Philae, or its name's whatever, its name's Philae. It's headed down, supposed to land here. It bounced. It bounced and the harpoon did not engage properly and it sort of sent it flying. And so we at first we didn't know where it was, and it was very scary. And people were like, oh shit, what happened? It like exploded or something. But then they looked over this review footage, and you can kind of see how these are like squares like this. That's because they were like taking imaging the whole time. Then they could like piece the imaging from different times to see it bounce. And notice how that shape is not the same as that shape. Right, so it's tumbling. So it's flying over the surface. And it's going this way, and you can see where it bounced down. Here's the 3 imprints. So it smacked down there, and then it flew over to the side, and it landed, basically it crashed into a wall, which would have been sick, except for that it happened to be laying on its side, and its solar panels couldn't get any light. Yeah, that's kind of, so we got some data, but not a lot. Here's where come on now. Here's where it's supposed to land, and that's where it landed. And like, honestly, that's like bad. Just like bad luck. Because look around at all the places it could have landed. It landed in the one place that's shaded. That's bad luck. Europeans tend to have a little bad luck with landers, but that's a longer story. Okay, this was gonna be great. Look how fun that would have been. To sit here and then like taking pictures. So beautiful. Okay, here's some of the pictures. So do you have an expectation of what it should look like already? What should the surface look like? I mean, we know these are black and white images. Or are they? Rocky surface. Why did we say that? Yeah, because then I said like it was like 5% ice at some places, right? So we expect it to be much more rocky, right? So this is what the surface looks like. Come on now. What? Yeah, and I'll show you the video in a second. So this is its little arm right here. And these are the pictures it was able to send home. So it was like, hey, I'm stuck against this cliff. Can you help? They were like, they actually did a lot of fun stuff. So they tried to like reuse the harpoon, and they tried to unfold the what are they called? Solar panels, because they have to unfurl. They thought like maybe if you unfurled one, you could get it to like roll over. It didn't work. But it's still pretty cute. And you know, This is like part of the exploration part of landing on something that you don't know what it's going to be like. It turned out that the ground had more rebound than they thought, right? So it's this dirty world, and you can see sort of in this in this world, you don't have the same sort of, if you look, for example, at geology on Earth, you might have sedimentation layers that are all one on top of the other, on top of the other, like layered like a cake. Here, it doesn't really look like it has that same sense of order, so to speak. It's more chaotic in the layering, but there are local areas of layering, right? So maybe this region was layered differently than this, right? Because layering is here, but layering over here is in a different location, right? Okay, so here's the video.
Colored or black and white?
No, they're all black and white.
I didn't know if it just was black.
No. That one is in fact black and white. Yeah, we don't always afford color, just because like if we're going to a place that looks like Mercury, what's the point, right? Okay, so this is one of the few videos that we got. Pretty rad. This is why I mean maybe it's dust. I like to think of it as snow. Like I think it's like more of like a cute way for it to gone out, like a wintry wonderland. But I guess there's also like sad implications for that as well. Maybe we shouldn't anthropomorphize spacecraft. Okay. Questions about this one? All right. Okay. So we talked about all of the parts of a comet. Do we talk about the tails? Okay. So let's say the orbit brings it close in and then it goes farther away. As it goes in, the blue here are gases that are liberated from the surface. What's an example of a gas that's liberated from the ice? Water vapor, right? Okay. And water vapor is part of ice. It's liberated, and then water vapor gets attacked by sunlight. Remember, we said that sunlight is really good at breaking up molecules. So what could you break that up into? Can you break water into? Hydrogen and oxygen. Good. Hydrogen is bigger, or sorry, oxygen is bigger? Which one's that bigger? Oxygen is bigger than hydrogen, or hydrogen is bigger than oxygen? Oh yeah, okay, right here. 1 and 8. I guess 16 is the total weight. So oxygen is 16 times larger, right? So the hydrogen, once it gets liberated from water, it just goes, wow, bye. And that's what makes this blue tail, right? Hydrogen. And then the oxygen gets hit a few more times with light, and it also is like, bye. What's up? Okay. So what's this one? This is all the dust. So we just showed all of that dirt, all of that stuff that was on the surface. That gets thrown off. But it does not immediately stream away. It's not being carried away by the sun's magnetic field. In fact, it's still orbiting the sun. It's just orbiting a little slower. And it just so happens that the way that that works is that they end up trailing this object and creating dust. So small grains will move down and large grains will stay right here. And they start like sorting, like if you go panning for gold and they make you do this, And then all the big stuff starts at the top, small stuff moves towards the bottom. That's essentially what's happening down the dust tail. So if you look at one of those earlier images, like this one here, okay, this is really thin, fine dust, whereas this is the thicker, stronger pieces of dust. And you'll actually be able to see, interestingly enough, if I look, right, this is the nucleus here. This is the orbit that the object is making in the sky and leaving pieces of dirt and dust all along. And then those smaller pieces are all making their own large dust pit. Okay, all right, we're almost there. So what happens to comets? They melt, yeah. Yeah, so they lose 1% or 0.1% of their mass every time they pass. They can only orbit a few hundred times before they completely turn off. If you really love these types of objects, you'll learn about things that are called like active asteroids, which is like an asteroid that's like kind of, or it was a comet at some point, or like a centaur. So it's like a spectrum, right? They're not like on or off. Like active comet, partially active comet, inactive comet, asteroid, right? Okay. They can become coated in too much dust so that it looks like an asteroid, but it's like really porous. There's ice under the surface. And maybe that's where you want to go mine. They can break apart and they can disintegrate. One of the first comets that I studied in graduate school was a sun grazer, which is a type of comet that literally goes like 1 or 2 just like radial distances from the sun away. And they happen more than once. They like go really close, they get really beautiful, and then they go back out again. I don't know if I have an example of it here. So this is the disintegration. You can see that this little piece broke into these pieces afterwards, right? And as they shatter, they show more of their surface area, which allows more evaporation, and then they can break up more. So sometimes that leads to complete disintegration, and they can smack into Jupiter. So you might say to yourself, oh, that's just dots. I've seen that before, Krismani, but you've never seen this before because this is Shoemaker-Levy 9. This is a comet, this comet, smacking into Jupiter. So some people like to say Jupiter's not a bully. It's like saved us from being hit by a lot of comets because it like sweeps them up. I will hear that argument, but he's still done a lot of mean things. Okay, so this is Shoemaker-Levy 9 with its little like pieces, and then this is the main piece hitting here, and these parts here. The cool thing is that we knew this was gonna happen. So there's a video where you can like watch, like it's not like a cool video, it's like from the 90s. So it's got like 7 frames, but it's like normal Jupiter, and then you see like light as it like smacks into the surface of Jupiter. It's pretty cool. Okay, there's the sun grazer I told you about. That's the sun. We put a little like disc over it so that you can't see the sun, because otherwise you wouldn't be able to see anything. It's called the coronagraph. And this is a solar flare that's coming out of the sun, but this is a sun grazer that's headed in, I guess, for a very hot date with the sun. And so it'll come out on the other side. Those don't last very long, I'll tell you that much. Mine didn't come out, it didn't come out the other side. Okay, where do they come from? Yeah. Hyperbelt, yeah, very close. Hyperbelt, and you're just missing one thing. The Oort cloud, there you go, good. So we have 2 sources, and they are outside of Jupiter, obviously of Jupiter, of Pluto. Okay, so you have this group of objects. Here's Pluto's orbit, and again, remember that each of these dots here is not to scale, not how it looks in real life, but this is the only way of showing you. You have all of these icy bodies that Pluto's a part of. And all of this here is represented inside of this little teeny tiny dot. Okay. So shrink down this cyan box into this exact size. See that? Okay, that's our whole solar system. And we have this giant cloud around us called the Oort cloud. And that is where you get your brand new comets. So typically, if you see a comet come from this region, it's probably their first time ever coming in to the inner solar system. These ones and these ones come from completely different parts of the solar system. They have completely different characteristics. And this thing was predicted by a guy named Oort. He saw 2 of these, and he correctly extrapolated that there should be about a million objects out there like this. And he was right. So sometimes science does good predictions, right? That seems like a really cool flex, right? You're like, I see 2 weird things. There must be a million of them. And then you're right, like 100 years later. Damn. Okay. Here's the asteroid belt. We talked a little bit about Jupiter. God. Sorry, guys. We talked about Pluto already, right? Pluto is what kind of object? I'll say planet. What kind of planet? A dwarf planet. Okay. You might also call it a Kuiper belt object. So it lives out in the Kuiper belt, right? And so this is a large region. New Horizons went, so that same spacecraft that went to Pluto went out to this other object called MU-69. I think we named it something different. And here's some other spacecraft that we sent out forever and ever and ever. I believe only these 2 are still talking to us. I don't think Pioneer 10 and 11 are still in contact. Okay. This is how the speed of these objects around the sun works. Mercury goes fast and Ares does not. So this is the orbital speed up here compared to the distance. Ares is a Kuiper belt object near the edge of Kuiper belt, the outer edge. Okay. Oh, this is how it's called. Arakoth. So we don't call it MU-69 anymore. I have to fix that other slide. These are the spacecraft images as we got close to this other one. You'll notice this theme here, right? That a lot of these comets, some of these Kuiper belt objects, they appear to be 2 circles touching, right? That is because when things are moving really slowly and they're icy and sticky, rather than hitting into each other and smashing, sometimes they hit into each other and they just stick. I don't know why, but that is what we see, right? This is another great image. What kind of features do you see? Crater, good. Where? The bottom here? No. Have you guys seen these before? No. This is Arakoth. I don't believe the colors are quite accurate. I believe this is highlighted to show contrast. You can see like there's a big impact crater right here. And there's all these small ones in here. So we can already tell that the ice composition is probably different from that of a comet, right? Because the fact that you do see these little ones means that it's definitely not as icy as a comet, because otherwise it would have just started to remove that material right away, right? Well, this is like right at the edge of our solar system, right? Yeah. So this is like in that final belt of objects. We probably, maybe if we get lucky, but we probably will not ever see an Oort cloud comet in the Oort cloud. You have to wait for them to get close. Okay. Other question about this one? We'll look at one more view. It's pretty good, right? No, it's a potato. But it's a pretty good potato. I mean, it's almost the same. If I flip between them, you almost got tricked. Okay. All right. Can't trust everything you read. Okay, we are making great time. We're going to be ready for formation on Thursday. Okay. Let's ask this question. Why is there a meteor shower every year around August 12th? Actually, what's today? Oh, just 2 days to the Geminis. I told you I'm okay. By the way, I'm like 8 hours ahead of you. Jet lag is for real. It's let's see. It is 2 a.m. for me. What? A month? Yeah, I know that we're okay. We're 5 days from the Leonids. There you go. That's better. Or in the past, if we go back before the election to the Taurids. Yeah, I was up until 5 a.m. Yeah, it sucked. That's why people were like, "How was Paris?" I was like, "It's great. I loved being there. Wonderful." Okay, and then I went to work. Um, we get it? Okay, not exactly. Uh, get your votes in on 5, 4, 3, 2, 1. Okay, so looks like there's maybe 2 camps. If you are in camp B or C, I want you to try and convince your neighbor of what it might be. If you're not in those camps, listen to someone from B or C.
That's fair.
Okay, revote when you're ready. Okay. All right. Anyone want to defend C? Or do you want to defend C?
The reason I picked C over B was if the comets also have a 1 year orbital period, that means if it was visible to us at such time, it would go with us off. So it
Right.
would be part of our sky, or it would never be part of our sky.
Yeah, right. So like the way that we thought about the Trojans that sort of trail Jupiter, or the Hildas that are, or the Greeks that are in front of Jupiter, right? Those are moving with Jupiter, and they're always either in front or in back. So for example, the reasons why comets come and go, they must have a different period than us, because they're either moving towards the sun faster than us and away from us, right? So this one's kind of weird then. Earth passes through the orbit path of a comet at the same time each year. Maybe that's just confusing, right? Okay, let's have a look. Hopefully I drew a picture. Oh yeah, I did it. Okay. So dust escapes the sand and dust-sized particles, and this spreads along the orbit. Okay. So this here are meteor showers. They sometimes appear to originate from a constellation. That's called the radiant of the constellation, right? So they appear to come out of it. That's just a particular part in space that we are passing into the direction. Okay. So as that dust hits the top of our atmosphere, it's usually going about 30 kilometers per second. That's about 180,000 miles an hour. And nothing can survive that. Okay. So if you're a little piece of dust with no propulsion system and no heat shield, you just burn up. And you make these beautiful streaks across the night sky. And sometimes they're green if you have specific elements in your dust. Sometimes they're blue or red, right? We saw that already when we saw some of the impact cratering stuff, right? So that's how meteors form, is these little pieces of dust. Grains of sand maybe are the largest ones that you might see. Usually it's about a piece of salt, right? Okay, so here's the diagram. Come on now. Okay, there you go. So I'll just try to simplify this a little bit. The sun's to the right-hand side. The nucleus is going that way. It's just like living its best life. It has no idea that it's losing weight. And the large day-old dust grains, they sit right here. But as they sort of like move, or as they like lag behind, they tend to form this larger dust tail. Now, this stuff back here, we may or may not be able to see. So these would be large dust grains, but they're not like bright and beautiful. It's this stuff here that's fine and thin, and these like small old grains, they reflect light really well, right? So we see this tail that seems to curve back and away. But as we look through, the tail is actually forming different particles of different sizes and different ages, right? Because as it moves through the solar system, large pieces come off, small pieces come off, and they all do different things, right? So even though it's heading along this path, it has this debris that's kind of spread out everywhere. Does that kind of make sense? And then we go that way through the debris stream, right? So we smash through the tail. So it's gone, but this year-old grain that's lagging behind it, that's what we pass through. Does that make sense? And that's a meteor shower. And that's why we have associated meteor showers with all of these ones here. I'm not going to attempt to do any dates now, but you may have heard of the Halley Comet. That was October 22nd. Halley Comet is responsible for the Oranids, which are a massive meteor shower, but we don't see the comet Halley except for, I think, every 60-something years. Right? But it's such a big comet, it left behind such a thick debris stream that every year when we go through it, we get a beautiful shower. Okay? There's like a little reminder. Yeah.
So the two question mark ones, are those, we're running into something from a comet that we just haven't found the actual comet?
Yeah. Yeah. And this is a really cool set of science, right? Where it's like, okay, it appears there's a meteor shower coming from that direction. I don't see where the body is, right? Like, did it melt entirely, right? Or did something else weird happen? Did it get knocked off course? Did it smash into something else, right? Okay. All right, let's just skip to this really quickly. We were talking about impact craters. People remember those things? Okay. We said that they smash into things, they make big holes, right? And we typically said that craters are about 10 times wider than the object that made them. And so we said on an object like the moon, right? You might have more small craters than large ones, right? Does that remind you of anything? Let's look at the size frequency distribution for impact rates. So here's how big the thing is, and here's how often it's going to smash into us. So up here is the stuff that happens every day, small. Here is the stuff that would end us, big. But it doesn't happen very often. That's good. Here's the stuff that causes the dinosaurs to go bye-bye. Not that frequently. 100 million years, that's pretty good. Last one was, anyone remember when the dinosaurs died? 65 million years ago. We got like another 35 M's to play with before we get hit again. We're chilling, right? That's not how that works, by the way. Okay. So you see that, stuff that hits you that's big, doesn't happen that frequently. And stuff that's small hits you frequently. Does that remind you of anything? What if I do this? Remember this plot from earlier today? Yeah, I mean, it's also a line, but I have big stuff over here, and I have small stuff over here, and this was the number of objects, right? So all I did is I took this image, number of asteroids versus the size, and I just flipped it. So in fact, we can see that the reason why we get hit by stuff that's small, right? The reason why we get frequently hit by stuff that's small, because there's a lot of stuff. And the reason why we don't get hit by stuff that's large is because all the big stuff is gone. That doesn't seem that deep, but that's pretty important. If there was a lot of stuff left over and we weren't getting hit by it, we'd have to explain that, right? But it also directly tells us what we're getting hit by, right? We're getting hit by asteroids because they follow that exact size frequency distribution. They match 1-to-1. So it's like the smoking gun. You like got the imprints on who did the shooting. Asteroid doing the shooting, right? Okay. Questions, comments, concerns? Okay, before we get into cosmic collisions, we'll end this section here. We'll talk about some formations of the moon on Thursday, and then we'll kind of go into formation as a whole. What I expect from you on Thursday is nothing. What I expect from you on Tuesday is homework 10 and your check-in. If I don't give you something back on Thursday, I will be upset. Okay? Anything else anyone needs?